Okay, today we started or continued the discussion of the momentum conservation equation, in which we noted that we're going to define our quantity B for the Reynolds transport theorem to be mass times velocity, which means that beta is the momentum per mass, or just the velocity vector. Now, for the system of fluid parcels, if we followed a system of fluid parcels, this is the left-hand side of a Reynolds transport theorem, that would be the time rate of change of mass times velocity for the system. But we know that the mass doesn't change. That's our mass conservation law. So this is just equal to mass times the rate of change of the velocity for the system, which is mass times acceleration. At this point, we can apply Newton's law and say this is equal to the net force, or the sum of the forces, that are acting on the fluid. And with that, we can write down then the Reynolds transport theorem for momentum, in which the left-hand side, the time rate of change of the system, is just the forces acting on the fluid, and the right-hand side is the time rate of change of the momentum in the control volume, plus now our flux terms. And these are really the critical ones to get right. The rate of change of the momentum in the control volume is, of course, important, but relatively easy to understand. Now we're thinking about fluxes of momentum. And so rho times velocity is like a momentum per volume. The volume crossing the control volume, control surface, is v dot dA. So this represents the fluid volume crossing the control surface. And this first part, rho v, is the momentum per volume. So together we get the fluxes of momentum across the control surface. And that's our momentum conservation equation for a control volume. Now, I want to point out the vector nature of this equation. First of all, note that the v dot dA is a scalar quantity. This is just a number, not a vector quantity. So the vector quantities are the force, the velocity that appears in the momentum here, and the momentum being carried across the control volume. So we can go to a component by component description, and I'll just write down the x component here. The x component would just be that the sum of the x components of the forces is equal to the time rate of change of mass times the velocity in the x direction, defined across the control volume, plus the integration over the control surface of rho vx. Now the v dot dA remains as it was, because that just represents the fluid that's being carried across the control surface. So here I think it maybe makes even more clear the three terms that depend on direction are the ones that are defining which component we're analyzing. And so if we were analyzing the y component, you would need to change the subscripts x, x, and x to y, and z would be the z components. Beyond that, it's really just a matter of setting up the approach carefully, and I'll talk a little bit more about that following the next lecture.